algorithm design from problem to solution in the realm of computer science and software engineering. Algorithm design stands as the cornerstone of efficient problem solving. It is not merely about writing code, but about crafting precise steps that transform abstract ideas into functional solutions. The journey from identifying an issue to developing a robust algorithm involves meticulous analysis, creativity, and technical expertise. This process shapes how we approach challenges in everything from data processing to artificial intelligence. The foundations of algorithmic thinking at its core, algorithm design begins with understanding the problem deeply. Without clarity on what needs solving, any solution will lack direction and effectiveness. A clear definition of inputs, outputs, and constraints forms the basis for designing meaningful algorithms. These elements act as guidelines throughout the development process. Consider a simple example: sorting numbers. Knowing whether the input size can be up to millions helps determine which sorting technique to use, like quicksort versus bubble sort. Effective algorithm designers often employ techniques such as decomposition, abstraction, and pattern recognition to break down complex problems into manageable parts. Decomposition: breaking a problem into smaller subproblems that are easier to solve individually before integrating them back together. Abstraction: focusing only on essential features while ignoring unnecessary complexity during initial stages of problem solving. Pattern recognition: identifying recurring structures within different types of problems that allow generalizable approaches. Mastery over these fundamental skills enables developers to tackle even seemingly insurmountable tasks by reducing them to simpler components. This mindset shift transforms daunting computational challenges into well-defined puzzles waiting to be solved through logical deduction and innovation. Evaluating efficiency through time complexity: an essential aspect of algorithm design lies in evaluating time complexity, the amount of time required relative to input size. Efficient algorithms ensure scalability across varying workloads. The Big O notation serves as a standard measure for expressing asymptotic growth rates, allowing comparisons between different algorithmic approaches objectively. For instance, an O(n) algorithm generally performs better than an O(n) superscript 2 counterpart when dealing with larger datasets due to linear versus quadratic scaling behavior. Understanding trade-offs between various complexities becomes crucial. Sometimes sacrificing space efficiency might yield significant gains in execution speed. Real-world applications demand careful consideration of both temporal and spatial requirements based on expected usage scenarios. Profiling tools help quantify performance differences empirically, guiding decisions toward optimal implementations tailored specifically towards given contexts. Design paradigms shaping modern algorithms: different paradigms guide algorithm creation depending upon nature of underlying issues faced by programmers today. Choosing appropriate methods ensures effective resolution paths emerge naturally from problem definitions themselves. Divide and conquer strategies recursively partition problems until they become trivial enough to handle straightforwardly without further recursion steps being necessary. Dynamic programming optimizes overlapping subproblem resolutions by storing previously computed results, thereby avoiding redundant calculations, significantly improving overall runtime efficiencies. Greedy algorithms make locally optimal choices at each decision step, aiming towards achieving globally optimal outcomes, although there exists cases where greedy choice may lead away from truly best possible end states. Backtracking explores potential solutions, incrementally building partial candidates, discarding those leading nowhere, ultimately pruning search spaces, effectively saving computation resources. Selecting right paradigm depends heavily upon characteristics inherent within particular application domains, requiring deep domain knowledge alongside strong analytical capabilities. Crafting effective data structures. Data structures form another critical component influencing success or failure of designed algorithms, since they dictate how efficiently operations get executed against stored information sets. Picking suitable structure aligns closely with chosen methodology, ensuring compatibility between implementation logic used alongside storage mechanisms employed simultaneously. Arrays provide direct access benefits, making them ideal for situations demanding frequent random element retrieval, though insertion/deletion operations suffer performance penalties compared alternatives. Linked lists excel particularly well regarding insertions and deletions, offering flexibility, missing out array counterparts, however lacking fast indexing capability. Trees facilitate hierarchical organization, useful, especially tree traversals, helping manage relationships among items conveniently. Hash tables enable rapid lookup times using hashing functions, converting keys into indices, facilitating constant time average case scenario performances, assuming good distribution properties hold true under normal operating conditions. Choosing correct combination of methodologies paired appropriately matched data constructs lays groundwork upon which successful implementations rest securely. Implementing recursive techniques effectively. Recursion offers elegant ways representing nested computations, simplifying otherwise complicated iterative loops into more readable formats, capturing essence behind many mathematical formulations succinctly. However, improper handling leads easily into infinite regressions unless base cases properly defined upfront alongside recursive calls carefully structured, maintaining progress towards eventual termination condition. Fibonacci sequence calculation illustrates classic example demonstrating difference between naive recursive methods suffering exponential time blowout, contrasted optimized memoization version cutting down redundancies substantially. Memory management considerations arise whenever implementing recursive routines because stack frames accumulate, potentially causing overflow errors beyond certain threshold limits depending platform specifics involved. Iterative rewrites sometimes preferred over recursive versions, primarily driven concerns around system resource limitations associated with deep call stacks impacting stability negatively under extreme circumstances. Balancing elegance provided by recursiveness against practicality demands attention, particularly high-performance computing environments where every cycle counts, critically affecting final product quality assessments made later during testing phases. Optimization strategies for real-world applications. While theoretical correctness remains paramount objective, primary aim extends also encompass real-world applicability, translating academic achievements practically viable products consumers interact daily with seamlessly. Performance tuning exercises frequently involve profiling existing systems, pinpointing bottlenecks, then applying targeted enhancements, eliminating wasteful activities, systematically increasing throughput gradually. Caching mechanisms reduce repeated expensive computations, storing intermediate results temporarily accessible quickly, subsequent requests benefiting greatly from reduced overhead costs incurred initially. Parallelism introduces opportunity, exploiting multi-core architectures, distributing workload evenly across available processors, accelerating completion times considerably, surpassing single-threaded capabilities significantly. Approximation algorithms serve helpful purpose, tackling NP-hard problems approximately, instead attempting find exact answers, usually impractical computationally intensive settings, preferring near-optimal acceptable approximations. Acceptable sufficient purposes. These optimizations require delicate balance struck between precision desired accuracy levels, achievable constrained hardware realities, prevailing environment, forcing compromises, accepted gracefully, transparently communicated stakeholders, involved project lifecycle management processes. Debugging and testing algorithmic solutions. Rigorous debugging procedures verify correctness, validating proposed designs meet intended specifications, accurately reflecting expectations set forth, originally conceived goals initially outlined. Blueprints drafted, early stages, planning phases. Unit tests isolate individual functions, confirming isolated behaviors, conform prescribed standards, ensuring atomic pieces function independently correctly prior integration occurring, higher level modules interacting cohesively, forming complete working programs. Edge case analyses identify rare yet impactful scenarios, exposing vulnerabilities lurking beneath surface appearances, revealing hidden flaws masked normally routine operations appearing benign, superficial inspection alone unable detect inherently subtle defects, silently creeping undetected, long periods unnoticed until manifest, suddenly catastrophic consequences ensue. Formal verification provides mathematically rigorous proofs establishing absolute guarantees correctness regardless external factors changing dynamically fluctuating unpredictable environmental variables affecting operational parameters, unexpectedly altering outcome unpredictably. Automated test suites maintain consistency across revisions, preserving regression-free state, preventing accidental introduction, new bugs disrupting established functionality, already stabilized, matured, sufficiently ready, deployment readiness. Evaluations commencing soon after release, cycles initiated following development milestones achieved. Continuous integration pipelines automate build/test/deploy workflows, ensuring latest changes continuously validated against growing suite assertions, checking compliance, maintaining reliability, integrity throughout entire software lifespan. Evolutionary trends influencing future designs, ongoing advancements reshape landscape, constantly evolving fields propelling forward, momentum driving innovations, emerging rapidly, transforming once static disciplines now vibrant dynamic ecosystems, thriving, perpetual motion fueled continuous discovery, research efforts ongoing. Machine learning integrates increasingly prevalent presence, reshapes traditional algorithmic landscapes, blending statistical modeling, machine perception, enabling autonomous adaptation, learning patterns, automatically adjusting behaviors, responding adaptively environmental stimuli experienced, encountered throughout operational lifetimes. Quantum computing presents revolutionary possibilities, leveraging quantum superpositions, entanglements, unlocking unprecedented speeds, solving problems considered impossible classical computers alone capable addressing feasibly, realistically within reasonable time frame. Blockchain technology introduces novel trust models, decentralized consensus protocols, securing digital assets, verifying transactions, cryptographically enhancing transparency, accountability across distributed networks, challenging centralized authorities traditionally dominating control structures, historically maintained status quo unchallenged, unquestioned. Cloud-native architectures prioritize elasticity, resilience, scalability, adapting fluidly shifting demand surges, spikes, traffic volumes, gracefully managing fluctuations without degradation, service quality, perceived users experiencing consistent responsiveness irrespective load variations affecting infrastructure utilization rates fluctuating irregularly, unpredictably. Staying abreast developments necessitates proactive engagement, participating communities, attending conferences, reading journals, experimenting prototypes, keeping pace, ever-changing technological frontiers shaping tomorrow's solutions, today's discussions. Conclusion: mastering algorithm design requires combining foundational principles with modern practices, continually refining skill set through practice experimentation. Learning from failures, successes alike, fostering growth mindset, embracing change, inevitable part, lifelong pursuit, excellence within field. Whether you're solving everyday coding challenges or pushing boundaries in AI and big data, the ability to create efficient, scalable algorithms will always be a defining trait of exceptional programmers and engineers.